Hi everyone, this is Mrs. Hanson, and we are going to be discussing Lesson 2.5, with discussing rational functions. And this video is 2.5.3 and 2.5.4. And our learning target for today will be for students to be able to graph rational functions by identifying vertical asymptotes, horizontal asymptotes, oblique asymptotes, and the intercepts of the function. Alright, so in the last video we talked a little bit about graphing a rational function at the very end, and we identified things like the vertical and horizontal asymptote and the intercepts. But here we are going to take this a little further and look at some more complicated examples where you might need to do some factoring in order to determine the position of those asymptotes and intercepts. So, one thing we're going to look at is the function f of x, and we need to determine the vertical, horizontal asymptotes and the intercepts for the function f of x, and then we're asked to graph the function and state its domain. Okay, I kind of like to work backwards and find the domain first. So, first of all, I know that 2x squared minus 8 cannot equal 0 because the denominator of any function can never equal 0. So I'm going to go ahead and solve that equation. 2x squared minus 8 cannot equal 0. I'm going to solve that for x. So I'll add 8 to both sides, get 2x squared cannot equal 8, divide by 2. I get x squared cannot equal 4. And I want to remove the exponent, the square here, so if I square root both sides, I get x cannot equal plus or minus 2. So remember, when we square root both sides of an equation, we need a plus or minus in front of our solution. Square root of 4 is equal to 2, so we get x cannot equal plus or minus 2. So this means that positive 2 and negative 2 are restricted from our domain. So our domain is from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Okay, we're using parentheses rather than brackets because, again, positive 2 and negative 2 cannot be used for x. Now, what this tells me is that positive 2 and negative 2, when I substitute them into this function for f of x, if I substitute 2 for x, or if I substitute negative 2 for x, we end up with the function being undefined. We're going to end up dividing by 0 if I substitute 2 or negative 2 in for x. So what this tells me is that my vertical asymptote is not just a vertical asymptote, it's vertical asymptotes because there's 2 of them. There's one at x equals 2 and one at x equals negative 2. For our horizontal asymptote, we look at the degree of each polynomial. So on top, my degree is 2. On bottom, my degree is 2. I get x squared over 2x squared. And on top, I have a coefficient of 1. And you have x squared over x squared. Since our degrees are the same here, then to determine our horizontal asymptote, we divide the coefficients. So if I divide the two coefficients, I end up with a horizontal asymptote at y equals 1/2. And so I've identified the vertical asymptotes. I've identified a horizontal asymptote. And now what we need to do, I've also stated the domain. What we need to do now is find the intercepts. Okay, and I will continue that work on the next slide. Okay, so we need to find the intercepts here of this function, and to do that, to find the zeros of the function, or the x-intercepts, that is where your numerator, the top function, is equal to 0. So I need to find the zeros of the function x squared minus x minus 12, okay, because that gives me the zeros of the function f of x. So if I set the numerator equal to 0, I can see that this is a quadratic trinomial. There's 3 terms, and it's quadratic because it's a degree 2 polynomial. And we are going to try and factor this in order to determine our zeros. So I'm going to get x times x, which gives me the first term x squared. Then I'm looking for 2 numbers that multiply to be negative 12, but also add to be negative 1. That is going to be negative 4 and positive 3. So we get, for zeros, if I set x minus 4 equal to 0, if x minus 4 is equal to 0, then x is going to equal positive 4. And if x plus 3 is equal to 0, then x is going to equal negative 3. Okay, so we have 2 x-intercepts, or 2 zeros of our function. And what we still need to do, though, is find our y-intercept. And our y-intercept is found by determining f of 0. So we substitute 0 for x to find the y-intercept. If I substitute 0 for x, I get 0 squared minus 0 minus 12 on top. And on bottom, I get 2 times 0 squared minus 8, which, if I simplify the numerator here, I'm going to get negative 12. And if I simplify the denominator here, I'm going to get negative 8. So negative 12 divided by negative 8 ends up with 3 halves. Okay, both 12 and 8 are divisible by 4, so if I divide 12 by 4, I get 3. If I divide 8 by 4, I get 2, and because both values are negative, we end up with a positive y-intercept. So 3 halves is also the same as 1.5, and our y-intercept is at 1.5 then, or 3 halves. All right, so we still have to graph the function. We've found the vertical asymptote, the horizontal asymptote, the domain, and the intercepts. And so now what we're going to do on the next slide is graph this function. Okay, so what we're looking at here is the graph of the function f of x. And I'm just going to go ahead and label a couple of things here. We said our y-intercept was at 1.5, or 3 halves, which is right here. We said that our x-intercepts were at negative 3 and positive 4. So here we have x equals negative 3, and here we have x equals positive 4. And what we also have is a vertical asymptote at negative 2. Okay, trying to make this as straight as possible here. So this is at x equals negative 2. There's a break. And at x equals positive 2. So if you looked at the table of the function, you would see that negative 2 and positive 2 are undefined in the table. And what we also have is a horizontal asymptote at positive 1/2. Now you can also confirm your horizontal asymptote by determining your end behavior. So if you made that table of values and let x get really big, like let's say let x approach 1 million or 10 million, 100 million, you would see that the y-coordinate then is approaching 1/2. And you could also see the same thing when x approaches negative infinity. So if you let x in your table approach negative infinity by saying x is negative 1,000, 10,000, negative 10,000, negative 100,000, negative 1 million, negative 10 million, you will see that the y-coordinate then in the table for those x values is approaching 1/2. So we have all the key components here on our graph of our function, and we're ready to move on to the next example. So what I want you to do here is to check your understanding of what we have just discussed. I want you to determine any vertical and horizontal asymptotes and intercepts for the function n of x equals 2x plus 5 over x minus 6. You have 4 choices, A, B, C, or D. go ahead, work out the question, work out the problem, and submit your answer. Okay, just to go through the answer here, we have a 0. The denominator is equal to 0 when x is 6, so therefore x cannot equal 6. That gives us a vertical asymptote at 6 as well. So since x cannot equal 6 and we divide, if we plug in 6 for x, we end up dividing by 0. That means our vertical asymptote is at x equals 6. So just glancing at the 4 choices of multiple choice, A would not be a correct response and B would not be a correct response because they're stating that the vertical asymptote is at 2. Moving on, if you look at your horizontal asymptote, because our degree is the same on top and bottom, the power, the highest exponent or power in the numerator and denominator is the same. Then we go to the coefficients and divide them. So 2 divided by 1 is equal to 2. So we're going to have a horizontal asymptote at y equals 2, which both C and D state that the horizontal asymptote is at 2. And if we want to find our y-intercept, let's find our zeros. If we find our zeros of our function or our x-intercepts, that is where the numerator is equal to 0. So if I set the numerator equal to 0, I get 2x equals negative 5, or x equals negative 5 halves. So our x-intercept, or our 0 for our function, is at negative 5 halves, which if you divide negative 5 by 2, you get negative 2.5. Which then eliminates option C because it's stating that our x-intercept is negative 3. So right now we do know that our answer is D, but to find our y-intercept, which I have not done yet, I find the y-intercept by substituting 0 for x. So I get 2 times 0 plus 5 divided by 0 minus 6, which ends up giving me 5 on top and negative 6 on bottom. And if you divide 5 by negative 6, that is approximately negative 0.833. So that gives us D as our correct response. Okay, so we need to discuss another type of asymptote here. We need to discuss what an oblique asymptote is. We've already discussed what a vertical asymptote is. Vertical asymptote goes up and down. Horizontal asymptote goes side to side or horizontal. And an oblique asymptote is diagonal. Now, we need to first determine how you can decide whether a function, a rational function, has an oblique asymptote. So, if f is a rational function, remember we defined a rational function as 2 polynomials divided by one another. So, both a of x and b of x have to be a polynomial function. Now, there's some other qualifications here in order to have an oblique asymptote. First of all, b of x has to have a degree greater than 0. So the bottom function, the bottom polynomial, has to have a degree greater than 0. And a of x and b of x can have no common factors other than 1. So when you're factoring the numerator and the denominator, you cannot have any of the same factors on top that you do on bottom. And if this all occurs, if b of x has a degree greater than 0, and a of x and b of x have no common factors other than 1, then the graph of f has an oblique asymptote if n equals m plus 1. So, the function for the oblique asymptote is the quotient polynomial q of x resulting from the division of a of x by b of x. So we're going to divide the numerator by the denominator. Use long division or even synthetic division if you want. And the quotient q of x is the function for the oblique asymptote. In other words, whatever your quotient is when you divide a of x by b of x, that gives you the equation for your oblique asymptote. So we'll say equation for oblique asymptote. Now, just to give you an idea here, just to discuss this n equals m plus 1, n is the degree of the numerator, m is the degree of the denominator, or the highest exponent, only if n equals m plus 1. In other words, what they're saying is that this degree on top has to be 1 greater than the degree on bottom. So there's another condition here in the fact that the degree of the numerator has to be 1 greater than the degree of the denominator in order for an oblique asymptote to exist. Now, if you look at this function f of x, the degree of our numerator is 2, the degree of our denominator is 1, so it is possible that an oblique asymptote exists. Now, the other factors that we have to consider is that b of x is greater than 0. The degree of b of x is greater than 0. Yep. The degree on the denominator is greater than 0. The degree is 1. And a of x and b of x can have no common factors. So if I factored out f of x, if I factor out f of x, on top it's x times x, on bottom we just have x plus 1. So we have no common factors, and some of you might be tempted to cross off this x with one of the x's on bottom, but you cannot do that because this x and this plus 1 are one factor together. And the only time you can cancel out a common factor is if you're multiplying in between the two terms, which there's an addition sign there. So just some things to consider. The oblique asymptote is then found by dividing x squared by x plus 1. So in other words, if I took x plus 1 and divided it into x squared plus 0x plus 0, our quotient here, if x goes into x goes into x squared x times. And then if I multiply x times x, I get x squared. X times positive 1 is positive 1x. If I subtract, I get negative 1. I get negative 1x, so I'm subtracting here. 0 minus 1x is negative 1x. I carry down the 0, so I'm going to get a plus 0. And if I divide x into this term here, I get a minus 1. So I'm carrying out long division here, and you can see that our quotient is x minus 1, hence why the equation for the oblique asymptote is x minus 1. So I know I ran out of room here at the bottom, but we'll look at this more in depth. You should already be comfortable with dividing two polynomials using long division. And we'll go through another example of a function that has an oblique asymptote in upcoming examples. All right, so we're looking at graphing rational functions, and we're asked to determine any asymptotes and intercepts for this function f of x, and then we're asked to provide the graph of a function and state its domain. So, similar to previous examples, we can determine our vertical asymptote. Our vertical asymptote is where we end up dividing by 0. So if x plus 3 can't equal 0, that implies x cannot equal negative 3. So our vertical asymptote is at negative 3. Our horizontal asymptote, again, is determined by comparing the degree of the numerator and the degree of the denominator. The top has a degree of 2 because the highest exponent is 2 here. On bottom, we have a degree 1 polynomial because the exponent on the x is 1. Can't write that small. 1. And so if we have a degree 2 over a degree 1 polynomial, then remember, when the degree on top is greater than the degree on bottom, there is no horizontal asymptote. Now what I'm going to do is I'm going to determine our oblique asymptote. If we have an oblique or diagonal asymptote, remember the degree of the denominator has to be greater than 0, which it is, since we have degree 1 on bottom. The degree of the numerator has to exceed or be bigger than the degree of the denominator by 1, which it is. The degree on top is 1 greater than the degree on bottom. And also there cannot be any common factors in the numerator and the denominator. Well, if I factor the top, I get x and x. And I'm looking for, since my quadratic is x squared plus x minus 8 on top, I'm looking for numbers that multiply to be -8 that add to be +1. Now the only numbers that multiply to be -8 are -8 and 1, +8 and -1, 4 and -2, and -4 and +2. Now, none of these options add up to give me +1, which means that x squared plus x minus 8, this quadratic, is not factorable. And therefore the numerator, x squared plus x minus 8, does not share a common factor with the denominator of x plus 3. So anyhow, we do have an oblique asymptote. And so what I'm going to do is I'm going to find out the equation of that oblique asymptote by dividing the numerator by the denominator. So I'm going to take the function on top and divide it by the function on bottom using polynomial long division. And if I do that, I'm going to get x plus 3 divided into x squared plus x minus 8. So if I divide x into x squared, x goes into x squared x times. If I multiply x times x, I get x squared. If I multiply x times +3, I get +3x. Remember, with long division, we subtract our columns, and I get x minus 3x is -2x. I'll carry down the -8. X goes into -2x, -2 times. So when I multiply -2 times x, I get -2x, and -2 here times +3 gives me +6. And when I subtract, I get a remainder of -14. Now, I do not care about the remainder in this case. The actual quotient of x minus 2 gives me the equation for my oblique asymptote. So my oblique asymptote is 1x minus 2, or y equals x minus 2. So we have our three asymptotes, our vertical asymptote, horizontal asymptote, obviously there was none, and we do have an oblique asymptote at x minus 2. Now we still need to state our domain, which our domain is going to be -infinity to -3, union -3 to infinity, because the only restriction on x was the fact that x couldn't equal -3. Alright, so what we're looking at here is going to graph the function. We've already have our asymptotes. Oh, one thing we haven't done is our intercepts, so I'll do that on the next slide. And then we've stated its domain, so we will also need to graph on the next slide. Alright, our intercepts need to be accounted for. And so our x-intercept, or intercepts, the zeros of our polynomial, or rational function in this case, but we have a polynomial on top and a polynomial on bottom. The zeros or x-intercepts of our function come from where x squared plus x minus 8, the numerator, is equal to 0. Now, I've already decided in the previous slide that this is not factorable, so we're going to have to use the quadratic formula to find the zeros of this function. So we're going to need to use negative b plus or minus square root of b squared minus 4ac all over 2a. And x equals, if you take the opposite of our b value, our a value is 1, b is 1, c is negative 8. So if I take the opposite of b, I get negative 1 plus or minus square root of 1 squared minus 4 times 1 times negative 8, all divided by 2, because 2 times our a value is 2. And we get negative 1 plus or minus, underneath the square root, we're going to end up with 1 plus 32, because negative 4 times 1 times negative 8 is positive 32. Divide by 2, and we get x equals negative 1 plus or minus square root of 33 divided by 2, which is in the end going to give me some decimals for my x-intercepts, because square root of 33 is not a perfect square. So when I take negative 1 plus root 33 and divide it by 2, I get 2.37. And when I take negative 1 minus root 33 divided by 2, I get approximately negative 3.37. So we're going to have two x-intercepts, one at 2.37 and one at negative 3.37. Now obviously I'm running out of space here, so I'm going to go to the next slide and calculate the y-intercept and then graph my function. Alright, so we have to determine our y-intercept. Our y-intercept is found by evaluating the function for x equals 0. So we have 0 squared plus 0 minus 8 all over 0 plus 3, which gives me negative 8/3. And if I take negative 8 divided by 3, that gives me negative 2.6 repeating. So we have a y-intercept at negative 2 2/3. I talked about our x-intercepts on the last slide, and now what we need to do is graph our function. Okay, so graphing the function f of x equals x squared plus 1x minus 8 all over x plus 3. Graphing that function, we determined that we have a horizontal asymptote at x equals negative 3. So right in between these two pieces right here is our vertical asymptote at negative 3. We determined that we did not have any horizontal asymptote. That can be shown in the graph by the fact that the limit as x approaches infinity, or negative infinity rather, approaches negative infinity. And the limit as x goes to positive infinity of the function is also equal to infinity. So remember that our horizontal asymptote occurs when the limit is approaching a specific constant or c value. And since our end behavior here is infinite, that is also an indication of why we do not have a horizontal asymptote. Our oblique asymptote was the equation x minus 2. So if you have x minus 2, my y-intercept is at negative 2, and my slope is positive 1. So I'm going to go up 1 and over 1, up 1 and over 1, up 1 and over 1, or down 1 and left 1. And you can see that we're going to have this oblique asymptote at x minus 2 equals y. That's the equation in slope-intercept form, where our y-intercept is at negative 2 and our slope is 1. I guess I could have put put in this equation y equals x minus 2 into Desmos and graphed it along with the function, but I just sketched it in myself. Now the other thing we need to confirm is our x and y intercepts. According to my algebra, I have a x-intercept at 2.37, right? X equals 2.37. We had another one at x equals negative 3.37. And our y-intercept is at negative 2 2/3, or y equals negative 2.6, repeating. So that is pretty much everything. We labeled our intercepts and our asymptotes. Our domain, obviously this function is not continuous. There's a restriction at negative 3. So our domain goes from negative infinity to negative 3 with a union of negative 3 to infinity. All right, here I would like you to check your understanding. I want you to determine any asymptotes and intercepts for this function r of x. I have a rational function r of x. I'm dividing two polynomial functions. The numerator is a quadratic, the denominator is a linear function, and we have 4 choices, A, B, C, or D. Go ahead and work out your asymptotes and intercepts and select your answer. Okay, what we're going to do here is we're looking at asymptotes. First of all, I know my vertical asymptote is going to be at x equals negative 2, because that is where we would end up dividing by 0. To determine if we have a horizontal asymptote, you compare the degree of the numerator to the degree of the denominator. Since my degree is higher on top, I have a degree 2 on top and a degree 1 on bottom. There is no horizontal asymptote for this function. To check for an oblique asymptote, remember there cannot be any common factors in the numerator and the denominator. This polynomial on top, x squared minus 3x plus 1, is not factorable because there's not two numbers that multiply to be 1 that add to be negative 3. And since there's not any common factors and the degree on top is 1 greater than the degree on bottom, and the degree on bottom is not equal to 0, it's greater than 0, we do have an oblique asymptote. So, to determine my oblique asymptote, I'm going to divide x plus 2 into x squared minus 3x plus 1. And if I do that, x goes into x squared x times, carry down the x squared, x times 2 is 2x. If I subtract, I get negative 5x, carry down the 1, and x goes into negative 5x minus 5 times. So I can finish carrying out the long division here. Negative 5 times x is negative 5x. Negative 5 times positive 2 is negative 10. And I do get a remainder of 11. I do not care what my remainder is. It is the quotient that ends up being the equation for my oblique asymptote. So my oblique asymptote is at x minus 5. So if we're looking at answers here, vertical asymptote at negative 2, an oblique asymptote at y equals x is what A says, so that's not correct. B, an asymptote, vertical asymptote at negative 2, oblique at x minus 5, so far so good. And D is going to be out because it says my oblique asymptote is at x squared minus 5x plus 11, which is not true. Now, what I need to do is probably determine the y-intercept next. If I substitute in 0 for x, I get a 1 over 2, because 0 here, and 0 here would just make all those terms 0. So 0 squared minus 3 times 0 plus 1 gives me 1 on top. and 0 plus 2 on bottom gives me 2, so my y-intercept is at 1/2. So right here, answer C is incorrect because it states that we have a y-intercept of 0. The other thing, so we know what the answer is, but in order to find our x-intercepts, you need to find where x squared minus 3x plus 1 is equal to 0. In the last example, because this is not factorable, x squared minus 3x plus 1 is not factorable, I'm going to do something similar to what I did in the previous example and use the quadratic formula. So in order to solve this, if it's not factorable, you're going to have to use quadratic formula. So down here at the bottom of the screen, I'm going to show that my intercepts are at 3 plus or minus root 5 over 2, my x-intercepts. So I'm going to get the opposite of b, which is positive 3, plus or minus b squared, which is 9, minus 4 times 1 times 1, all over 2a, which is 2. You get x equals 3 plus or minus square root of 5, because 9 minus 4 times 1 times 1 is just 4. So 9 minus 4 is 5. Divide all that by 2, and you get 3 plus root 5 over 2 and 3 minus root 5 over 2. So B is the correct response to this problem, and then obviously you could always confirm your asymptotes and your intercepts by graphing this function r of x.